Hello everyone, it's me Matthew again, and welcome back to our last module on graphs. Today we're going to go over the hidden Gator problem. So let's get straight into it. And remember, our 3 steps were to understand the problem, come up with a solution, and to optimize. So let's get into the problem statement and see what this is talking about. So in the Marston Library, there are n students labeled from 1 to n, and there's a rumor that one of these students is secretly a Gator. If the Gator exists, then the Gator knows nobody, and everyone except for the Gator knows the Gator. And there's at most one student who is a Gator and satisfies both properties. Okay, so we're given a vector, no, of knowledge relations, which are also vectors. A knowledge relation, no I, AI, BI, denotes that the student labeled AI knows the student labeled BI. And we note that BI does not necessarily know AI. And this makes sense, right? Because I can know LeBron James, but LeBron James doesn't necessarily know me. So if a knowledge relation doesn't exist in no, then such a knowledge relation does not exist. And our goal is to return the label of the Gator if the Gator exists and can be identified, or we return -1 otherwise. So let's jump into some examples now. So n is equal to 2, so there are 2 students, and the knowledge vector, or the no vector, has this no relation in it. So student 1, no student 2. And the output is student 2. So the explanation says that all students, student 1, know the Gator, student 2. And the Gator, student 2, knows nobody. So the Gator is student 2. And we see that student 2 satisfies these 2 conditions, which is why it's the Gator. Now we go on to the next example, n is equal to 3. And we see that the no vector has student 1, no student 2, student 2, no student 3, and student 3, no student 1. And the output here is -1, and the explanation says that every student knows some other student, so there can't be a Gator. And this makes sense, right? Because if the Gator exists, then the Gator knows nobody. But here we see that every student knows someone else, so we know immediately that these conditions aren't satisfied and there's no Gator within these 3 students. Now we look at the third example, and it's pretty similar to the previous example, except n is equal to 4 now. And the explanation says that the first 3 students know another student, and there's a student A4 that knows nobody. So we see that the first condition here is satisfied, but the first 3 students do not know A4, so we can't determine that A4 is a Gator, right? So if all the students knew student number 4, then A4 would be a Gator, but since they don't, then we just return -1 because we can't identify the Gator. And we look on to the last example here, and we see that when there's one student, the knowledge relation is empty, and the output is 1. And the explanation says that there are no students that do not know student 1, and student 1 doesn't know anyone, so student 1 is a Gator. And so let's just look at this first statement here. So there are no students that do not know student 1. And if we think about it for a bit, then this is kind of equivalent to everybody knows the Gator, right? Because there's not one student who doesn't know the Gator. So when you think about it in that sense, there's only one student, and the other students that aren't student 1, there's no student that doesn't know student 1. So in that sense, we can say that that condition, the second condition, is satisfied. And we can also say that the first condition is satisfied since there's no relation, knowledge relation, where student 1 knows anyone else. All right, so now that we've gotten that underway, I think the first thing that I want to note is that this kind of looks like a graph theory or a graph problem, right? Where we can say each student is an individual node, and if there's a no relation, then there's an edge from student AI to student BI. So if we go ahead and look at this first example, there are 2 students, so there are 2 nodes. And in this no relation, we can say that there's an edge from student 1 to student 2. And we can kind of say that this no relation then is an edge list. And remember, an edge list is just it's a vector or a list of edges which contain one vertex and another vertex. And that just says that there's an edge from student 1, in this case, to student 2. And in this specific problem, we can say that it's a directed graph, right? Since there can be an edge from student A to student B if student A knows student B, but if student B doesn't know student A, then there's not necessarily an edge to them, from student B to student A. So I think that'll help us come up with a solution. And if we just go ahead and look at the constraints, we see that there's going to be at least one student and at most 1,000 students, and no dot length is at least 0 and up to 10,000. And then now we'll see that the no relation, so no I dot length, is always going to be 2. And so all pairs of no are unique. And this is just saying that one student can't know the same student twice, right? So here, student 1 knows student 2. There's never going to be another student 1 knowing student 2. So no parallel edges. And furthermore, AI is not going to be equal to student BI. So there's not going to be any self loops, right? Like the Gator is not going to know itself, and a student isn't going to know itself. And then the last one, AI and BI are always going to represent a student from 1 to n. So now that we've taken a look at the constraints and seen that this problem is sort of similar to being modeled like a graph, let's go ahead and look at some of these conditions here. So before we get into it, we want to model this as a graph, right? So if student A knows student B, then there's an edge going from student A to student B. And remember, in a directed graph, an out degree of a vertex is just how many edges are coming out of it, right? So if we look at these conditions here, if the Gator knows nobody, then there's no knowledge relation where the Gator is listed first, right? So from there, we can say out degree of V is equal to 0. And we'll just say V is an arbitrary node in this graph. And then we're going to want to say that everybody knows the Gator. So if we look at this example here, student 1 knows student 2, so there's an edge from student 1 to student 2, which means that the in degree of student 2 is 1, right? And there's going to be n minus 1 students, or n minus 1 students that know this Gator. So we say the in degree of V is equal to n minus 1, since all the students have degrees mapping to this Gator, and that just means that they all know the Gator. So we know what conditions need to be satisfied for a vertex or for a node in this graph, and we know that the no vector is just going to be an edge list. So we have a representation of this graph, and what we want to do is find a vertex that satisfies both of these conditions. So let's just come up with solution 1 for now. So we want to find one student that satisfies both of these conditions, right? Well, an easy brute force solution would just be to enumerate through each student and then iterate through this no vector and see if there's a student such that the Gator knows nobody, so the out degree of V is equal to 0, and everybody knows the Gator. So enumerate through all students and then enumerate through edges to verify or to find a student with sufficient conditions. All right, and if we do find a student with these conditions, then we'll just return their index or their label, and if we don't, then we'll just return -1 since we haven't found them. So let's just go ahead and try it out for example 2, see if it works first. So we're going to start at student number 1. And so the first thing we see in this edge list is that student number 1 knows student number 2. So the out degree is not going to be equal to 0. And so once we find that, we can just kind of skip student number 1 since we know that they're not going to be a Gator. Then we go to student number 2. And then we see that we iterate through the no vector again. And we see that student number 1 is not student number 2. So the out degree of student number 2 is 0 so far. And then we also see that the in degree of student number 2 so far is 1, since 1 knows 2. But then we go to the next edge in the list, and we see that 2 knows number 3, or student number 3, And so we know that there's an edge coming out of student number 2. So this condition of the out degree being 0 is not satisfied, so we skip it again. Then we go to the last student, we see 1, 2, right? We see that this condition hasn't been violated yet, and we just, we continue to increment the in degree. So we get to this edge, and we see 2 knows number 3. So we increment how many vertices are the in degree of student number 3. But then we see, again, that student number 3 knows student number 1, so out degree is not satisfied. So it seems like our solution works right now, so let's just go ahead and code it up. And yeah, so like we said, first we're going to want to enumerate through all students. So how many students are there? We start from 1, and then we go all the way up to the nth student, and we increment the students along the way. And then we're going to want to enumerate through each edge to find a student with sufficient conditions. So what conditions do we want? Again, out degree of v is equal to 0. So we want them to know no one. So let's just create a bool called knows nobody, and let's just set this equal to true at first. And then we're going to want to keep track of how many people know the Gator. So int knows student, and we're just going to set that equal to 0 for now. Then, like we said, we're going to enumerate through all the edges to find a student with sufficient conditions. So we're going to go std vector int, and let's just call this a k relation, right? And this is going to be in the no vector. And then, like we said, we want to check if the out degree of v is equal to 0 first. Yeah, and we check if k relation 0. So if this student is equal to the current student, then what we're going to want to do is knows nobody is equal to false, and then we're going to break. And in the second case, if they aren't the first student, then we're going to want to say if k relation 1 is equal to I, then we're going to increment knows student. And yeah, that's all we're going to do for this second case. And if by the end of this enumeration we see that both of these conditions are satisfied, then we're going to want to return the student. So we say if knows nobody and knows student is equal to n minus 1, right? Because we want every other student to know this student. So if we see that these conditions are satisfied, then we'll just return the label. And if by the end of this entire for loop we haven't found a student that matches it, then we're just going to return -1. And let's just do this for one more example to make sure that our entire solution actually works. So in this case, n is equal to 2, and so we start the for loop, and we start at the first student. We initialize these variables, then we iterate through the edges in this edge list. So we're at student number 1, and we immediately see that this first condition is true. So student number 1 knows somebody. So we say knows nobody is equal to false, and then we break out of this for loop. Then we go to this if condition, and we see that knows nobody is false. So then we don't return, and we go to the next student. So now we're at student number 2, and then we reset these conditions, and then we go through this no relation. So student number 1 isn't student number 2, so this isn't satisfied. So then we go to the next relation, or next if statement, and we see that the student here is equal to the student we're currently on. So there's one more student who knows student number 2, and we increment knows student. And yeah, that's all the edges in the edge list. So we move on from this, and we say knows nobody is still true. And how many students know student number 2? Well, it's just n minus 1, right? So we said that there was one student that knew student number 2, and that's equal to 1. So we return 2. So it seems like our solution seems to work. And let's just try it against the rest of the test cases. And if there's anything wrong, well then we'll fix it. Okay. And in that case, nope. Everything's perfect. Our solution works. So congratulations, we came up with the solution. Now let's just go ahead and test, or not test, but let's record the time and space complexity of this and see if there's any improvements that we might need to make. So all we're really doing in this algorithm is doing this for loop right here, right? So we're iterating n times, and within this for loop, first thing we're doing is initializing these variables. Then we're going through every single no relation in this no vector. And within this for loop, these are all just O of 1 operations, and this is also an O of 1 operation. So let's just go ahead and look at the time complexity of this first for loop here, right? We said that these are all O of 1 relations, so we don't need to worry about what's going on in here. But like we said, we noted that this is like an edge list of a graph, right? So if we let m be the number of edges in the graph, then we can say that this is an O of m operation since we're iterating through all of the edges. And then these are all just O of 1, so we don't need to consider these. And then we see here that we're doing n iterations, and within each iteration we're doing an O of m operation. So it's clear that this is just O of n times m time complexity. So O of n times m. And in terms of space, well, we're not really allocating any extra data structures, so this is just O of 1. So we can see that this is O of n times n, and there might be some sort of optimization for this since n and m, when they get quite large, it won't be the nicest algorithm. So we might want to look and see if there's anything else that we can do. And in this case, there is. So let's just go ahead and say solution 2. So we see that the bottleneck here is iterating through the entire edge list every single time we do, or we iterate through every single student. And what we want to observe is that we want 2 students, or we just want 1 student that has out degree v is equal to 0 and in degree v is equal to n minus 1. So one thing we can try to do is iterate through the entire edge list once, and we can update the out degree whenever we see a student who's first here, and then we can also update the in degree of a student whenever we see that a student is second. And we iterate through that entire edge list, right? And then at the end, we iterate through one of the whatever we're keeping track of, right? Let's just say we have an array that's keeping track of both of these, and we just want to find 1 student who satisfies both. And if we do, then we return that student, otherwise we return -1. So it seems as if this algorithm might be a little bit better in terms of time complexity. So let's just write that down again. Enumerate through no vector, and update out degree and in degree of each student. And I want to note that we're going to keep these in some sort of array. So then we're going to enumerate through one of the arrays and find a student which satisfies both of these conditions. So satisfies conditions. So this is just going to be an O of m operation, right? Since we're iterating through this no vector once. And then this is also just going to be an O of n operation, since we're just going to get each student, look at what they have in the out degree and in degree, and if both of these are satisfied, then we return them. So in terms of time complexity, we see that this looks like it's going to be an O of m plus m operation, or yeah, in terms of running time, which is already better than n times m. And in terms of space complexity, since we're storing the out degree and in degree of each student, then this is going to be O of n. So it seems as if this is going to work, and let's just try it out on one of these examples here first before we code it out. So enumerate through no. student 1 has a out degree of 1, and student 2 has an in degree of 1. Now student 2 has an in degree of 1 as well, and student 3 has an in degree of 1. And then student 3 has an out degree of 1, and student 1 has an in degree of 1. Yeah, and so once we iterate through each of their out and in degrees, we see that there's no student with an out degree of 0, so we return -1. So we see that this is working for one of the examples, and our thought process seems to make sense, so let's just go ahead and code up our solution now, see if it really works. So we're going to want to keep track of the in degree and out degree of each node, so let's just create one vector for now, and let's just call this the in degree map, and this is going to keep track of the in degree of each vertex, or of each student. And we initialize it to be n+1 so that we can access each student with their label, and it'll just make life easier for us so we don't have to subtract 1 and add 1 to make sure that it's within the bounds of this vector. And then we're also going to do the same, but this time it's going to be the OD map, and this is just going to keep track of the out degree of each vertex, or of each student. And now we're going to enumerate through no. So for each vector of ints called k relation in no, right? Like we said, we're going to increment the out degree of the first student, so OD map, and then k relation 0. We're going to increment that, and then we're going to increment the in degree of the second student, so ID map k relation 1, and then we increment. So after this first enumeration through no, we're going to enumerate through one of the arrays and find a student that satisfies both conditions. So let's just iterate through OD map, right? So for each student, and we start at 1, and then we end at n, and then we say if this student has an out degree of 0, so OD map of I, if that's equal to 0, and then we say the in degree of this student is equal to n-1, so ID map I is equal to n-1, then we found a student that satisfies both of these conditions, so all we need to do is return their label. Otherwise, if we never do find a student that satisfies both of these conditions, then we're going to return -1. And so let's just try it out on this fourth example to see if it actually returns a student. So first we declare these maps, and then we iterate through each vector in k relation. In this case, the no vector is empty, so we don't do any iterations. Then we go to the first student, and we see that the OD map of I is equal to 0, since these are all initialized to 0. And we see that the in degree of the student is also equal to n-1, which is 0. So then we just return the first student. So theoretically, this example should work. And let's just go ahead and test it out against the other test cases and see if our solution works. All right, perfect. So now we've come up with a solution and optimized it. Pat yourself on the back, that wasn't easy. So yeah, we were able to reduce it from O of n plus m to O of n plus m from O of n times n. And we observed that just by taking note that these two conditions needed to be satisfied and that there was an easier way to check for them. So yeah, that's the entire problem. I hope you liked it and understood it. That's all from me today. Thank you. Bye.